Okay, let's dive right into this. Welcome back to The Explainer. Today, we're looking at one of the most massive, highly sensitive engineering projects happening on the planet right now. We're talking about Egypt's El Dabaa Nuclear Power Plant. Picture this. Giant cranes, cranes capable of lifting entire skyscrapers, moving these incredibly heavy, zero margin for error nuclear components right into place. It's literally transforming a huge patch of desert into a high-tech energy hub. And, this isn't just about pouring concrete, it's a total mega energy transition for the entire nation, shifting from standard civil construction straight into advanced nuclear installation.
4,800 megawatts. That is the sheer, mind-boggling total electrical output we're expecting from this facility once it's fully up and running by the year 2030. To actually pull that off, Egypt is building 4 advanced Generation 3+ reactors, with each one pumping a massive 1,200 megawatts into the grid. Now, what really makes these third-generation reactors stand out? Well, it's their state-of-the-art passive safety systems. They're bringing absolutely the highest levels of modern efficiency and security to the African continent.
To really put that power into perspective, let's think about the Aswan High Dam. For decades, the High Dam has been the historic, absolute, undisputed champion of Egypt's power generation, right? But get this, El Dabaa is projected to produce roughly 35 billion kilowatt-hours annually. That means this new nuclear plant will produce more than double the electricity currently generated by the High Dam. We are looking at a single facility that is going to fundamentally redefine the entire country's energy capabilities.
So, to really wrap our heads around the scale of all this, we're going to break it down into 4 parts: technical assembly, operation timeline, economic returns, and powering national projects.
All right, starting with part 1, technical assembly, a race against time.
Right now, the project is deep into a highly intense, super-monitored phase of nuclear installation. The crews are racing against the clock to hit these really strict deadlines, but, and this is absolutely crucial, with zero margin for error. You just can't mess around with this kind of sensitive technology. So where do things stand today? Well, for Unit 1, the really heavy lifting is officially done. Both the RPV and the reactor core have been successfully installed, which means Unit 1 is completely ready to receive its actual nuclear fuel. Meanwhile, Unit 2 just received its massive RPV recently on May 21st, and those giant cranes are prepping for its super delicate installation as we speak. And at the exact same time, all the way over in Russia, the highly specialized steam generators for Unit 3 are already being manufactured. It's this perfectly synchronized, massive multi-unit operation. Now, you might hear terms like RPV and reactor core tossed around in the reports, and honestly, they kind of sound interchangeable, but they actually do completely different things. The reactor pressure vessel, or RPV, is basically the giant, incredibly durable outer steel shell. Think of it as the container that holds the whole shebang. The reactor core, on the other hand, is the critical inner component. That is where the actual nuclear fuel lives and where the nuclear reactions physically take place. So, during the assembly, those massive cranes have to carefully, perfectly lower this inner core right down inside the huge steel RPV shell.
Moving on to part 2, operation timeline, the road to 2030. Let's look at the actual chronological path to getting this power online. By the first half of 2026, we're going to see some major preparation milestones crossed off the list. And that leads right into 2027, which is a massive turning point, because that's when the test operations for Unit 1 begin. Assuming all goes well with the tests, Unit 1 will officially launch into service in 2028, adding its first 1,200 megawatts directly to the national grid. Fast forward to 2030, and the momentum really peaks. The full plant, all 4 reactors, will be completely finished. By that target year, this single facility is projected to supply roughly 12% of Egypt's total electricity needs. No small feat.
Of course, building something of this magnitude takes an absolute army of workers. And what's really impressive here is that 80% of that workforce is Egyptian. It's a huge local undertaking. The reports point out that Egyptian companies have fully taken over the execution of the civil construction. The other 20% is made up of highly specialized foreign expertise, mainly from Rose-aly, because they're the ones handling the really complex manufacturing of the nuclear components. Plus, there are intensive local training programs happening right alongside construction, ensuring that a fully capable local Egyptian workforce is ready to manage the plant for the long haul.
Okay, part 3, economic returns, ending fossil fuel dependence.
30 billion cubic meters. That is the colossal volume of natural gas imports that Egypt is going to save every single year once El Dabaa is fully up and running. Think about that for a second. This project isn't just about keeping the lights on. It's about a fundamental shift to clean energy that solves a really, really expensive problem. Right now, huge amounts of costly natural gas and oil are just burned to generate electricity. But by switching over to these Gen 3 plus nuclear reactors, Egypt literally eliminates that specific reliance on imported, polluting fossil fuels for its power. It is a real game changer.
So let's break down the math. By simply not importing all that oil and gas, Egypt instantly saves roughly $3 billion annually in foreign exchange. But the economic impact actually multiplies from there. Because Egypt won't have to burn its own domestic natural gas supplies just to make electricity, those local resources can suddenly be exported, or they can be used to fuel local manufacturing. When you combine those direct import savings with that brand new revenue potential, you are looking at an estimated $7 billion in total value being redirected into local industry and exports every single year.
Finally, let's wrap up with Part 4, Powering National Projects.
This is where the abstract concept of megawatts turns into vital, everyday infrastructure. Massive new agricultural megaprojects like the new Delta and Tashka rely completely on giant water pumps and huge pivot irrigation systems. And all of that requires immense, uninterrupted electricity to essentially turn the desert green. On top of that, just look at the country's new transportation network. We're talking high-speed electric trains, the massive Cairo metro expansion, the brand new monorail, and vast networks of electric buses. None of this modern transit runs on gas, it all runs entirely on electricity. So Dabaa is quite literally the engine that's going to pump the water for agriculture and physically move millions of people every single day.
Which brings us to a really crucial final thought I want to leave you with today. When you consider the billions of dollars saved annually in foreign exchange, the massive new transit systems being powered, these vast agricultural projects getting watered, and the establishment of a totally reliable, clean energy grid, how exactly will Egypt's complete transition to Gen 3 plus nuclear energy reshape its role in the regional economy over the next decade? It is a fascinating question about energy independence and the massive economic ripple effects that follow. Thanks so much for joining this explainer, and we will see you next time.